Let's look at a proof of Liouville's theorem, and it says if f is entire and bounded, then it's constant, which doesn't seem real intuitive at first. Entire, well, I mean, that's kind of a given because you can't have singularities or it couldn't possibly be constant. Bounded is maybe the less intuitive thing, but if you think about even just the equation of a line, it's always unbounded. The only time it's bounded is if it's a constant. So when you think of it that way, maybe it's not that crazy to think about. We're going to use Cauchy's integral formula for this proof, which is just this here. And I'll include in the description a link to Cauchy's integral formula and the proof of it if you're interested. And but basically it's used for if you're I'm going to write the 2 pi I over here just for a second instead of here. And basically if you have an integral that has a singularity, so I'd say it has a singularity at 2, well then you can plug that in and you can figure it out over here. It's going to be 2 pi I times f evaluated at 2. And so you can put, you know, any a in there that, well, if, you know, it can be any a, but if you're trying to figure out a singularity, then, you know, this Cauchy's integral formula is it's so much easier to do 2 pi I times wherever the singularity was evaluated at a than it is to try to figure out how to actually do this thing. So just keep in mind we have f here and here. It's pretty much static here. This is kind of where we use it, but it's still f. And f is, we're assuming it is entire. This is not, but f itself is. And the situation here is, so if you had a singularity at a, and you're trying to take the integral of the closed contour around that, well, that's what you can use Cauchy's integral formula for. But Cauchy's theorem, which I'll put a link for that in the description too, says that you can make that contour anything you want, any size. You can make it small, you can make it different shapes. In a little bit, we're going to choose to make it a circle with a at the center just so it facilitates parametrizing. But the first thing we're going to do is we're going to integrate this with respect, it's not integrate, take the derivative with respect to a of this thing. And so what we get is this on the left, and over here, this of course is constant. This, so really, you know, we're only moving the a position. This just, you know, is just sitting here. So this isn't moving, so this isn't moving. So they're constant with respect to a. And so when we take the derivative of this, we can, by Leibniz's integral rule, which I'll include that too. So a lot of things in the description that you might be interested in checking out. But Leibniz's integral rule says if we're taking, you know, dA of this thing, we can move it to the inside of the integral. And so that's what I've done here. Since f of z is relatively constant, then this is all we need to do. And when you take the derivative of that with respect to a, you get this. And then you can set f of z back up here. So that's all I've done here. So let's see, where does that get us? So basically here we have the derivative with respect to a of Cauchy's integral formula. The strategy is going to be essentially we're going to bound f of z, and then we're going to prove that that makes this constant. It's just easier. It's easier to bound this than this, and it's easier to see the result of the bounding here than here. That's kind of the idea behind using this. Okay, so that's going to be our strategy. we're going to bound this, and it's essentially going to show that the first derivative is 0, which would show that this is constant. So we're going to put a bound on the modulus of f of z, because that's how you bound a complex function anyway, is just through its modulus. So everything's going to be done through absolute value. And so then we're going to parametrize this by thinking, if this is our singularity A, we're going to make a circle around it, because by Cauchy's integral, or sorry, Cauchy's theorem, we can do that. And so the parametrization of f of z is just going to be making z this. So if you think about it, this, if we hold r constant, this will be a circle as theta is moving. So this is going to be a parametrization using theta. This would be a circle with the center at the origin. This is a circle centered at A. So that's kind of the thinking here. We're doing that because we can choose to. And so we replace z with that. And then dz d theta is just going to be this. And then we put the d theta over here. And so we can replace dz with this. And so dz has been replaced by that. Okay, and then the i's can cancel. And here they're not even really canceling each other. They can cancel anyway, just because the absolute value of I is 1. So those are gone. Then we have this with the power 1 over itself with the power 2. So we end up just having this. And now we can move the absolute value inside by the triangle inequality for integers, and I'll put a link for that in the description too. So basically that's been done here, except it's just broken up. And by the triangle inequality, we can say that now this is going to be less than or equal to this with the absolute value moved inside. Now the absolute value of r is just r, and that's a constant, so it can come out here. So here that is. And the absolute value of e to the I theta is just 1. So we get from here to here with inequality. And now we just have f of z parametrized by theta. And now the strategy is to bound this with our m, which is what we did up here. So this is less than or equal to m, which means if we take this and substitute m for this, then we get this inequality. So this is greater than or equal to this. And now m is a constant, so it can come up here. And we end up just taking the integral from 0 to 2 pi of d theta, which is 2 pi. Those cancel. We get m over r. So overall, now we have the statement that the derivative, the first derivative of f evaluated at A, is less than or equal to this. So we're almost there. So this is what we have. And now we're going to multiply both sides by r, so we get this. And now notice that r, we could take that contour as big as we want, and this equality has to hold. So r can go to infinity, and the inequality holds. And the only way that could happen is if this first derivative is equal to 0. So we don't need the absolute value anymore to make this statement. And if the first derivative is 0, then f is constant. And that's the proof. And keep in mind that A, it has to be inside the close contour, but we can make that as big as we want. So we could cover the whole complex plane with it. So we could put any z value in here we want. So f of z is constant, and that is our proof.